There are a lot of different ways to model fire behavior in Frame. I'll show you through some of the main approaches there, and to do that we'll start out by loading and compiling parameter files using the same data that we used in the previous session. As we've seen, the basic function for modeling fire in Frame is the function ffmrun. This is used in various combinations in other ensemble functions. We'll run that here, then load the database. By itself, ffmrun doesn't give you an accurate picture of fire behavior, because what it does is it compacts all of the details for the community that you're modeling into one vertical transect. So it removes all horizontal information. Now the database that we're loading here is actually a list of 7 smaller databases. The first of these is the runs database. Runs gives us 3 fields. The first of these is rep ID. Where this comes from is the db recreate option in ffmrun. If we set that db recreate option to true, what that means is every time ffmrun is run, it appends a new model run to the same database. Each of those new model runs will be then given a new rep ID. The next column there is run index. So for every rep ID there are 2 run indices, and we can see what they are by looking at the third column, canopy included. Where canopy included has a value of 1, it means that the uppermost stratum, that could be a tree canopy or it could be a shrub canopy in a heathland, for example. If the value is 1, then that canopy is included. If it's 0, then the canopy's been removed and the wind field beneath it has been readjusted. What this is for situations where you have an active crown fire, where fire is moving through the canopy faster than the ground fire, and Frame then recalculates a second run to look at how that increased wind field, the increased exposure to the wind at the ground, will affect surface fire behavior. The second database is called strata, and what that does is to give us the different plant strata that have been created in the clustering algorithm earlier on, and which strata are being considered for that rep ID. FrameSummaries now gives us information on the fire behavior within those plant strata. So we can see there are 4 entries for rep ID 1. That means an entry for each of the 2 plant strata multiplied by each of the 2 run indices. For each of those, that gives us the flame length, flame angle in radians, and the flame height for those strata, with and without the plant canopy, the topmost plant canopy in place. The sites database gives us a description of the input values describing the site, so the weather and terrain values as well as surface litter. So for rep ID 1 we have wind speed in meters per second, temperature degrees Celsius, slope in degrees. We have the fuel load, which is the weight of surface litter in kilograms per square meter. There's a value there for the mean fineness of leaves. Now, I suggest not fiddling with this. This was based on an old equation from MacArthur, so at the moment I just leave it at its default value rather than using an unreliable model. Mean fuel diameter is the diameter of leaf litter. The average diameter, which is 5 millimeters. Dead fuel moisture percentage of 0.1 here indicates 10% dead fuel moisture. The ROS table gives us rate of spread in meters per second for each stratum. As we can see here that in both run indices, fire was only spreading through surface and near surface fuels. Therefore there was no active crown fire, and only run index 1 will be used for reporting from this run. Surface results give us fire behavior in the surface litter as modelled by Dr. Burrows' surface fire behavior model. That gives us the flame length in meters, flame angle in radians, and flame height in meters, based on those two different wind speeds in meters per second. As you can see, the wind speed for run index 2 is higher, as you would expect if there was no tree canopy protecting the fire spreading through the litter. The IP table is a large part of what sets Frame apart from other fire behaviour models, because it reveals the inner workings of the fire behaviour calculations. Each line in this table is 1 second's fire spread through that specific plant species. So we can see at the left hand side there's the rep ID column. All of this is from the same rep ID. The run index will tell us whether there was a plant canopy involved in those calculations or not. Level is the plant stratum. Path type tells us whether fire is spreading just within an individual plant crown or through the stratum itself. If it spreads through the stratum, it treats the stratum as if it's one long plant crown. Now within that stratum we have individual species, and this segment index, seg index, there tells us what time step of fire spread we're looking at for that moment there. For each time step we have X and Y coordinates for the base of the ignited leaves, X0 and Y0, and the upper end of the ignited leaves, X1 and Y1. These are measurements from the center of the plant. So X0 is meters to the right of the plant. So if it's a negative value, then that means the segment is beginning at the left. Y0 is meters from the base of the plant crown. The length of that segment is shown in the next column, and the flame length that results from that is shown for each second. To illustrate what that looks like in a real-world scenario, this is a burning leaf of bracken. We can see that the area marked as A shows the leaves that are burning in the bracken. The arrows indicate the spacing between the leaves, which is one of the inputs to Frame there to describe that plant, as well as details of the individual parts of that leaf. The area B shows us leaves that have already burned, but they have now extinguished. Now the flame duration of those leaves was again determined by traits of those leaves. Now I'm saying leaves, but these are all leaflets, all parts of a compound leaf. If we consider them as individual leaves, though, just for the sake of the example, we have a series of traits that we have given Frame to tell it how long each individual leaf will burn for, the size flame that it will produce, and how difficult they are to ignite, how long it will take for them to ignite at certain distances. So when we combine that with the spacing of those leaves on the plant, we get this sort of result. We can tell that at this time step there are now 4 leaves burning and 2 leaves below that that have extinguished. When we look at the combination of the flamelets from those 4 burning leaves, we get C, which tells us how far the flame will extend from the burning leaves, and the total flame length is the combination of the area in A and C. We can then look at how that plays out in a specific example. Here we have a tree with a hollow marked by A over the top of a grass tree, a bulgur grass tree marked by B. That tree has clearly burnt, the grass tree has burned, and the details of the fire spread that are given in the IP table are shown at C and shown at scale in the white lines at B. So we can see, if we look at the detail in C, that the distance from the plant center is shown on the x-axis and the height of that flame segment is shown on the y-axis. Initially we start out with a leaning flame that moves towards the center of the plant. Then after a while the base of that flame goes out, and that becomes the new base for the next flame segment. eventually we get a taller flame that ultimately dies down and flame angle changes again. So as we saw, FFM run compresses all of the landscape variability into the one location. If we want to get a realistic picture of fire behavior across the landscape, we need to use what are called pseudo transects. If you think of the actual field transect, we run out the field transect and measure vertical transects at regular points along that line. And each vertical transect gives us a slightly different picture of the forest. It's the combination of them that we put together to give the parameter files. But fire behavior at each point will be different, and weather parameters will also vary very slightly. There'll be gusts of wind and slight variations in weather across that area. So what Frame does then is offers ways to vary these parameters within distributions. And the first of these functions is one called Probfire. We can see with Probfire that we can enter into this parameters that describe the variability in each of the inputs. And we also have this number jitters. Jitters just basically means the number of replicates that we're going to run, the number of points that we will model fire for in the landscape. Now, quite often we might want to use a large number of replicates to get a good picture, but here we'll just run it quickly with 10 points. We'll vary slope, temperature, dead fuel moisture content and wind around those mean values in a normal distribution described by that standard deviation and truncated within range values. We can also vary the live leaf moisture within similar distributions and vary the height of plants within standard distributions that are truncated, again to values that we give it. Leaf variability we can vary in thickness, just with random variability within a certain range there. This will take a little bit longer because we're running now 10 replicates instead of 1. Now for this example we're going to use some datasets that come with the Frame package, and in addition we will use the package ExtraDister to allow us to calculate variability within these distributions. These datasets describe an alpine ash forest, a Eucalyptus delegatensis forest, that was used in examples in the 2021 Methods in Ecology and Evolution paper. As we run through Probfire, you'll see notifications for the number of replicates remaining. You can turn that off or on in the function there. Now Frame, as you will have noticed, takes a lot longer than traditional fire models that we're used to using, which generally are made up of 1 or 2 equations. In contrast, we've seen the detail that Frame uses to calculate in the ignition paths. This is replicated for each plant and within each stratum of the forest. So the number of calculations to get from the forest floor to the forest canopy, and to at the same time consider how that affects the wind field within the forest, means that to run a calculation like this for each point is roughly 500,000 calculations instead of just the one equation. To look at the output from this, we'll load the database again, and we're going to use a function called FrameSummary, which combines outputs from a number of the databases to pull out the ones that we're most interested in. So we can see here for each of the 10 replicates, we have details giving us the slope, the wind in kilometers per hour, dead fuel moisture content, the air temperature varied around that mean, the height of the flame from the plant, from any burning plants there, and the length of the flame in meters from burning plants, also the angle in radians, rate of spread in kilometers per hour for the whole fire site. This extinct field tells us whether fire was actually burning there, spreading, which is a value of 1, or not spreading, which is a value of 0. In addition to that, we have these fields describing the surface flame from surface litter, length surface and height surface, as well as angle surface. Then FH and FL give us flame height and flame length overall for the fire ground for that replicate. And the fields zeta and epsilon give us descriptions of the flame for calculating radiation. We'll also use this function stratum, which summarizes a few other details, which we'll look at a little bit later, and summarize some of the key fire behavior parameters, just looking at quantiles of flame height here. I'll add another field to the table that I've calculated from FrameSummary, and what this field looks at is just simply whether plants were burning or whether it was only litter burning. If we look at that field, we can see that plants were burning in each run. Where that's calculated from is the field's height plant, length plant, which tell us that if there was a value greater than 0, then plants were burning. Let's have a look at the outputs from those Probfire runs using the runs table, which was from FrameSummary, to give us a picture of flame heights, and looking at the differences in rate of spread between different strata. So looking at that fire behavior, we can see that in all instances plants were burning, so there's no comparison to be made there, and they produced flames with a median height of just under 3 meters there, and a fair bit of variation. Fire spread, however, did not occur in the elevated or canopy strata. Even though elevated plants were burning, fire did not spread between plants there, so it didn't adjust the rate of spread. The rate of spread was increased in this instance by fire spreading through near-surface plants, where it spread considerably faster than through the surface litter. Surface litter fire spread was slow, as predicted by the model of Dr. Neil Burrows. Now I've pulled out a few important values of fire behavior to put into this statement here that summarizes things. First of all, we are looking at the percentage of time for which parallel attack is possible over the fire ground. So this is a firefighting term. The most aggressive forms of firefighting are either direct or parallel attack. Otherwise, firefighters need to fall back to backburns. So if you can conduct parallel attack, then you're able to aggressively control that fire. Now that's only possible for over 70% of the fire ground. So probably that decision would not be made, and they would need to fall back to backburning. And part of that is because there is occasional torching of flames up to close to 4 meters in height. The rate of spread here is 0.38 kilometers per hour. Now that will again be important for decision making around control of that fire. Probfire then is a way of comparing potential fire behavior for a design set of weather conditions, a particular point in a day, allowing for variability in those conditions and in the vegetation there. We may, however, want to look at how fire behavior varies across a wide suite of conditions, such as across a day of fire spread that we're modeling, or across a set of representative fire conditions. In that case, the function that has been built for this is Weatherset frame. What Weatherset frame does is uses a data set of weather conditions. In this case, we'll use Tuart weather, which is loaded with the package. And for each point in that time series, we can run a given number of replicates. We'll be using 5 replicates here. Weatherset essentially does the same thing that Probfire does, but for a series of weather conditions instead of just for the one. design set of conditions. And because this will obviously take longer still, we have a progress bar that tells us how that's progressing. To look at the results from that, we'll again load the output database and use FrameSummary. We'll mutate an extra field onto the end of that to capture the time of day, and then produce two plots giving us fire behavior across that time sequence. When we look at the graphed outputs, we don't see a very strong trend in there. There's slightly faster fire spread in the afternoon. The first part of the day, or third of the day, there's very slow spread for a while. Flame height seems to vary very little over the course of the day. There's a lot of variability within each time step though. The reason for this is that weather is not driving the variability in fire behavior across the site. It's fairly consistent. What drives it is variability in the vegetation. The final analysis I'll take you through uses the drivers function. Now, drivers is a similar approach to both of the previous analyses in that it uses pseudo transects across the landscape. The drivers function differs from these earlier analyses, however, in that it uses a series of equally ranged weather and terrain variables. The goal here is not to look at variability for a design set of weather conditions like Probfire frame, or to look at weather fire behavior across a sequence of weather conditions. Here it is to understand what the drivers of fire behavior are. Essentially what we're doing then with the drivers analysis is to ask the question, how will fire behavior change if it's burning on this slope, or at this dead fuel moisture content, or at this wind speed here? So we produce a lot of different contingencies and replicate those varying vegetation parameters for each set of replicates, and then that leaves us with quite a large number of replicates in the end. So this is a long, slow function that's best run overnight. As with the other analyses, we'll look at the results this time by loading the database using FrameSummary to capture the main parameters that we're after, and then graph those results. In this case, we'll graph the results using facet grid because we've got a lot of different contingencies that we'd like to compare. Firstly, if we look at the structure of these graphs, what I've done is divided the results into columns representing the different slope classes that we examined. For each row, there is a different dead fuel moisture proportion. There were 3 different dead fuel moisture values we tested. Along the x-axis of each individual graph we have wind speed, and on the y-axis on this panel we have flame height. Now what we can see is, in general, there's not a lot of variation across these graphs, except for particularly in the drier litter components, the stronger wind speeds and the higher slopes. We get this scattering of rare points, of very large flames, what appear to be crown fires occurring. So we can see that in general, flame height doesn't vary hugely, except that at these strong wind speeds on steep slopes, there are occasional crown fire events, but quite rare. The other thing that we can see is that if we look at the 10-degree slope, we'll note that flame heights increase above about 30 km/h wind. So there is a steady increase in flame heights there, although it's quite small compared to the overall change in height from the crown fires. We can see probably a doubling in flame height as the wind speed increases there. In this forest community, it appears that the more interesting results are happening with changes in rates of spread. So the first thing to notice is that if we look on the left-hand side here, with the downslope spreading fires, we have a continuing upward trend shown in the green, whereas the more we move to the right and the steeper the slopes, the more the upper end of that trend drops down. The second thing we can see is that there's a bifurcation in results. So although the majority of points follow the green trend, there's a second line of trends on all of the panels that doesn't follow that trend. So what's happening here? These outcomes are related to the stratification of vegetation. So we have three main strata over the surface litter. There is a layer of near surface vegetation, a layer of taller shrubs, and then a very tall layer of trees. What's happening in these cases, by the looks of things, is that there are two possibilities. One is that fire is increasingly spreading in the shrubs as the wind speed increases, and that's the green line there. But in other cases, fire isn't able to ignite the shrubs and it's spreading beneath those shrubs, and those are the points at the bottom. So why does the line drop down? Why does the trend drop down when we have strong winds? Wouldn't stronger winds and steeper slopes give us faster spreading fire? Well, if we think about the mechanics of fire spread, as that wind speed increases, particularly on a steeper slope, the flame angle is closer to the slope angle, which means that it's not reaching as high above the ground. So in those instances, say for example we look at the 20-degree slope, once we get to wind speeds over about 30 kilometers an hour, approaching 40 kilometers an hour, what Frame is telling us is that the angle of the flame is becoming attached to the slope, too close to the slope to be able to ignite the shrubs, and so the rate of spread now drops down. Now that is good as a theory, but Frame can take us beyond the need to guess. It can tell us exactly why those results occurred. For example, there's this confusing seeming conflict as to why there was the tallest flames at the strongest wind speeds on the steepest slopes, and yet those were also instances where the rate of spread had dropped down. So what's going on? If we look at two of the tables from that modelling run, look at flame summaries and the rate of spread table, then we can start examining those points. First of all, if we look at the flame summaries table, we can filter that to find the highest flames and find the rep ID where those flames occurred. We can see that those flames were burning in the canopy. If we now go to the rate of spread table and filter it for that rep ID, we can see that there was no rate of spread recorded for the canopy. So we know from that that the canopy was igniting, but fire was not spreading through the canopy. This is what's termed a passive crown fire. To find out what's actually happening with these plants, we can have a look at the ignition paths database. When we run that, we get the list of ignited segments. We can filter that for our rep ID again. And as we look through that, we can see that when the shrubs, the elevated layer, Divisia latifolia, ignite, we end up with some of these flames that at times are nearly 12 meters in length. So that's a very big flame. Now these 12-meter flames, the top of those flames is, the top of the plant is 6 meters above the ground, so these are very tall shrubs in this instance. And now we have a Eucalyptus delegatensis that's ignited over the top of that, and the base of that is around 26 meters above the ground. So that is a big gap, but an 11 meter, 12 meter flame has managed to ignite across that gap. The last thing we'll note here is that there is a small section of stratum spread in the canopy. That means that fire was spreading tree to tree. There was a very short period of active crown fire, but as you can see, it only lasts for a few seconds. This is why it wasn't long enough to affect the overall rate of spread of the fire.